Now we will start with the theory of free undamped vibration system. So before we proceed further, we'll start with the derivation of simple harmonic motion, which we have already seen in our physics. So first we'll plot the displacement time plot over here. So as you can see, the motion which is repeating after a regular interval of time is known as the simple harmonic motion. Now let us consider that the motion is taking place in a circular path in such a way that the point A dash is now moving in a circular path to point A through an angular displacement theta. So this vertical displacement is small x and this OA is the capital X. Now take projection over here. So you can say that the projection of this particular system or point A is shown in the figure. So projection of point A is shown in the figure and this is the displacement time graph. Now point A dash initially it was at this position. After rotation in the anti-clockwise direction, its another position is shown, that is over here, and likewise you are having the various position of point A or point A dash, and you'll get this particular graph, and this graph is known as the sinusoidal waveform and it is the simple harmonic motion. So motion starting from this point, amplitude, this is the vertical distance which is known as the amplitude. So it is maximum at this point, becomes 0, again becomes maximum in the negative side, then again becomes 0, and this motion is repeated after a regular interval of time. The angle that is made by OA with the horizontal or the angle turned by this A dash is theta, as we have already seen. So we can say that from this right angle triangle, that is OBA, sin theta will be equal to opposite side divided by hypotenuse. That is opposite side is small x, hypotenuse is capital X. So that is written over here. That is sin theta is equal to x upon x. Small x is the displacement in meter. X dot, it is dx by dt, that is velocity in meter per second. X double dot is nothing but acceleration in meter per second square. So these are the various terms which will be required to be used. Now we know that the definition of angular velocity omega is, it is rate of change of angular displacement. So it is theta upon time. Theta is the angle and t is the time. So this is angular displacement divided by time. So theta will be equal to omega multiplied by t. Now we have to derive the expression for simple harmonic motion. This is known as one cycle. So this has started from this 0 point and again the next cycle is starting from this point onwards. So it has completed one cycle over here. Now x is equal to x sin theta from the previous equation, which we have already seen, that x is equal to capital X into sin theta. So therefore, in place of theta, we can substitute omega t. So in place of this theta, we have substituted omega t. Differentiate with respect to x. So dx by dt will be equal to derivative of x sin omega t. So this is x as it is, derivative of sine is cos, and again by chain rule derivative of omega t. So derivative of sine term is cos, but instead of t we are having omega t. So again derivative of the term omega t. If it could have been only t, then derivative of sine t could have been only cos t. But instead of t we are having omega t. So again we have to take into consideration the derivative of omega t, and that is the chain rule. So omega is a constant, so it is only derivative of t with respect to t, that is nothing but 1. So that we have mentioned. So this x as it is, cos omega t as it is, omega as it is, derivative of t with respect to t is 1. So ultimately we can say that dx by dt is nothing but x dot, and that is equal to, just rearrange the terms. So this omega we have written in front of this capital X, so it is omega capital X cos omega t. So the first expression is that of the displacement, The second one is that of the velocity. So derivative of displacement is nothing but velocity. Now again differentiate with respect to t. So here we should have differentiation with respect to t and not with respect to x. So again differentiate with respect to, we can say t. So it is dx dot by dt. So dx dot by dt is equal to derivative of omega x cos omega t. Now minus omega x we have written. Omega x we have written over here. Derivative of cos is minus sine omega t. And again by chain rule, the derivative of omega t. So omega multiplied by x, which is a constant, it is as it is. Derivative of cos is minus sine omega t. And by chain rule, again derivative of this term, that is omega t. Again, omega is a constant, so it is derivative of t with respect to t. So we can say that derivative of dx dot by dt is nothing but acceleration, that is rate of change of velocity is nothing but acceleration. So this is x double dot. Here it is rate of change of displacement, so it is velocity, that is x dot, which we have written. And this we have already seen in our previous slide, that is x is displacement, dx by dt is x dot, that is velocity, dx dot by dt is nothing but acceleration, that is x double dot, minus omega x. So minus omega multiplied by omega, that is omega square x sine omega t as it is. Derivative of t with respect to t is 1. So this term is 1. This omega multiplied by omega, that is omega square with negative sign, and this x sine omega t as it is. Now we know that this x sine omega t from our equation 1 is nothing but small x. So x dot minus omega square x, transfer this minus term on this side, it will become positive. So it is x double dot plus omega square x is equal to 0. So this is the second order differential equation of simple harmonic motion. Now the various terms which we have used in vibrations. So the terms which we are going to use are period of vibration or time period. Now it is the time interval after which the motion is repeated. So as we have seen in the previous case, the motion again starts from 0 after completion of the one cycle. So if you consider this as the start of the cycle and this is the end of the cycle, then this is one cycle, and again now the cycle is repeating. So the time which is required from this motion up to this motion, whatever the time that is required, this is the time period, that is capital T, for the completion of one cycle. And after this particular point, the motion is again repeating. So this is the one cycle and the motion is repeated after that particular cycle. So whatever the time that is required, so here it is 0 second. So this is the start of this particular cycle, and up to this, suppose we require 3 seconds to complete this motion, that is from this point up to this point, then 3 seconds is the time period for this particular cycle. So it is the motion completed during one time period. So this is in 3 seconds, whatever the motion that is completed, that is known as one cycle. So in 3 seconds, the motion that is completed is this particular one. So this is the cycle. Now frequency, it is the reciprocal of this time period. So 1 upon 3, it is the frequency. So it is the number of cycles which are completed in 1 second. So this is 3 seconds, this is the total time period. So frequency will be equal to how many cycles they have completed in one time period or in 1 second. So that is known as what? The frequency of that particular motion. Amplitude, the maximum displacement. So you can see this distance is nothing but the amplitude in positive direction, and this is amplitude in the negative direction. So this is the amplitude, that is the displacement from the mean position. So what are the position that we have shown over here? This is the mean position. So this horizontal line which we have drawn is the mean position. So these are the various important terms which are considered, which are to be considered in vibrations. Now there are various types of the vibratory motion. One is the forced vibration, then free or natural vibration, and damped vibration. So forced vibration means what? Or first we'll start with the natural vibration and then we'll go for the forced vibration. So in case of the natural vibration, there is no external force that is acting on the system. For example, our heart, it is vibrating with some vibration, with some frequency of vibration is there, and that is the natural frequency of vibration. Then in case of the forced vibration, we are having some external forces which are acting on the body and they are causing the vibration in the body. For example, in IC engine, the internal combustion engine, the engine is having four strokes: suction, compression, expansion, and exhaust, and there are vibrations which are created because of the unbalanced forces which are present in the system. Now damped vibration means what? When the vibrations, they are decreasing in their magnitude. So for example, you can have the motion like this. So you can see, if this is the, then vibration amplitude over here is larger, then it goes on decreasing, and again it has decreased, and then finally it will vanish, correct, after some time. So because of the spring or because of the dashboard or shock absorber, we can say that the vibrations are diminishing or they are decreasing over every cycle. So over here, why amplitude is larger, magnitude of the amplitude of the vibration is larger. Over here it is decreasing, over here again it is decreasing, and like that. So you'll get the exponential curve if you draw the curve through this top point. So that is the damped vibrations. So their amplitude is decreasing over the period of time, then that is known as the damped vibration. Otherwise it is undamped vibrations. Now, the derivation of spring mass system we have already seen. So you can refer to that particular video where we have derived this expression. So expression for the spring mass system is that it is a second order differential equation, that is x double dot plus k by m, x is equal to 0. So if you compare that particular one with the simple harmonic motion which we have derived already, then omega square will be equal to k by m, and we can say that omega will be equal to square root of k by m. Omega is angular velocity and that is 2 pi multiplied by frequency. So frequency is nothing but it is the number of cycles which are completed in 1 second. So frequency will be equal to 1 upon 2 pi square root of k by n, cycles per second or oscillations per second, or it is also known as hertz. So this is the derivation which we have already seen. Now we have to represent the kinetic energy and potential energy. Now we know that in our strength of material chapter, we have already seen that the area under the load deformation diagram is representing what? Strain energy. Because strain energy is nothing but what? It is the energy stored due to deformation. So if it is a gradually applied load, so gradually applied load means what? The load starts from 0, increases gradually up to W. Then corresponding deformation of any elastic body like spring is supposed to say X. Then this diagram, if you drop a perpendicular from this, then you will get a right angle triangle. So this area under this particular load deformation diagram, or we can say that the area of this triangle is nothing but the strain energy that is stored, that is U. So energy stored due to the deformation is known as the strain energy. Now, before we proceed further for the derivation, let us derive the term stiffness, which we have already seen in our design of spring. So K is the stiffness, that is equal to load per unit deformation. That is, for deforming 1 mm spring, how much load is required, correct? So if you want to deform, if you want to compress the spring, or if you want to stretch the spring through 1 mm, then how much load is required? That is known as the stiffness of the spring. As far as this particular diagram is concerned, it is W upon X. So in place of load, we are substituting W. In place of deformation, it is x. So it is W is equal to K multiplied by x. In strength of material, instead of x, we are using delta. So W will be equal to K multiplied by x. Now kinetic energy is 1 half mv square. In place of velocity, it is x dot, so it is 1 half m x dot square. Now here we are representing kinetic energy and potential energy. As far as strain energy is concerned, it is only related with the potential energy and not the kinetic energy. Just we are seeing how the kinetic energy we are going to represent in the derivations of dynamics of machinery. Now this potential energy, which is the form of, or rather strain energy, which is the form of potential energy, that we will represent now. So potential energy, it is nothing but the strain energy stored. Again, joule or Newton meter is the unit of energy. It is the area under load deformation diagram. That is 1 half base into height, or 1 half load multiplied by deformation. This height we have represented over here, that is nothing but W. It is the height, and base is nothing but x. So that is deformation. X is the deformation. So this height is nothing but load. This base is deformation. So this is 1 half W into x, or W multiplied by x. Now in place of W, we can substitute K multiplied by x. So we can say that potential energy is 1 half Kx square. So as far as our next part of the derivations they are concerned, we are going to represent kinetic energy directly by 1 half mx dot square, and we are going to represent potential energy, if at all it is present in the system due to spring or any other elastic body, then it is 1 half Kx square. Now the equation of simple harmonic motion and spring mass system, we can derive them by using the method which is known as another method which is known as the energy method. Now as far as the law of conservation of energy is concerned, total energy remains constant. Total energy of the system remains constant. It will get transformed from one form to another form. So we can say that the summation of kinetic energy plus potential energy has to remain constant. Kinetic energy, just now we have seen that it is 1 half mx dot square. Potential energy 1 half kx square, and that summation should remain constant. So either it will be 2 plus 5 or 5 plus 2, but that summation will always be a constant. Now differentiate with respect to t. So du by dt will be equal to 1 half is constant, m is constant, derivative of x dot square, plus this 1 half is constant, k is constant, derivative of x square. Now derivative of x dot square is 2x dot, and again derivative of x dot, because instead of t square it is x dot square is there, so again you have to apply the chain rule. Derivative of x square is 2x, but instead of t it is x is there, so again derivative of x with respect to t. So this is nothing but, now we know that as the energy, total energy remains constant, derivative of constant is always 0. So this 2 will get cancelled up. M as it is x dot, derivative of x dot is x double dot. This 2 and this 2 will get cancelled up. K x dx by dt is nothing but x double dot. You can take x dot common. So if you take x dot common from these two terms, then it is only mx double dot plus kx that will remain. This x dot will cancel with this 0. So 0 upon this x dot, because this is in multiplication. If it will go on this side, it will be 0 upon x dot, that is 0. So ultimately what we will get is mx double dot plus kx is equal to 0. Now divide throughout by m. So this m will get cancelled. So this x double dot plus k by mx is equal to 0. So this is the expression for the spring mass system. So in the previous case we have derived it by free body method, free body diagram method, and now this is the energy method. Now here also if you compare this with the equation of S.H.M, you will get omega square is equal to k by m, or omega is equal to square root of k by m, and frequency is 2 pi f. Omega is equal to 2 pi, so frequency will be equal to 1 upon 2 pi square root of k upon m hertz or cycles per second. Now we have to see the analogy between linear motion and angular motion. Now this is the most important part of this chapter. So x is the linear displacement, corresponding angular motion analogy is theta. So x is linear displacement, theta is angular displacement. This is in meter, this is in radian. X dot is the linear velocity, that is v also. Analogy in angular motion, it is omega or theta dot, that is angular velocity radian per second. A or F is the linear acceleration, x double dot. So here it should be x double dot. So here two dots are there. So x double dot is the linear acceleration, theta double dot is the angular acceleration. It is also denoted by alpha. Here it is A or F, and this is meter per second square, this is radian per second square. In the linear motion, mass m is expressed in kg. Corresponding value in angular motion is I, that is mass moment of inertia in kg meter square. Kinetic energy, just now we have seen, it is 1/2 mx dot square. In angular motion, it is 1/2. Replace this m by I and x dot by omega or theta dot. So it is 1/2 I theta dot square. Potential energy is 1/2 kx square in linear system. Replace this k by kt, that is torsional stiffness, and linear displacement x by angular displacement, that is theta square. So 1/2 kx square is replaced by 1/2 kt theta square. So if it is a linear motion, then you have to use these values. Okay, whatever the values which we have written over here. So linear stiffness is W by X, that is load per unit deflection. Torsional stiffness is, in place of W, it is torque. In place of linear displacement X, it is theta. Correct, like that. So this is the analogy between linear motion and angular motion, which we'll have to use consistently in our derivations. So various types of the vibrations, there are longitudinal vibrations, torsional vibrations, transverse vibration, correct, like that. So if this is the vertical shaft and if it is doing motion in the vertical direction, then it is a longitudinal vibration. So motion of vibration is parallel to the axis of the shaft. If the vibratory motion is oscillating like pendulum, that is this motion is perpendicular to the, almost perpendicular to the this vertical axis of the shaft, then we can say that it is transverse vibration. Now instead of that, if it is twisting, so if you see in the top view, this is the top view, if it is doing vibrations like this, correct, it is oscillating like this, then it is known as the torsional vibrations. So this B is known as the main position and A and C are known as the extreme positions over here. In the next lecture, we'll start with the examples on these vibrations. So before we go for the example, just remember these expressions for the transverse vibration. That is omega n is square root of k by m, or 1 upon 2 pi square root of k by m, or square root of g upon delta, and time period is 1 upon frequency. Just remember this. For torsional vibrations, instead of k by m, it is square root of kt by I. Replace k by kt and m by I. So natural frequency of vibration will be 1 upon 2 pi square root of kt upon I in hertz, and time period is 1 upon frequency. Now, according to torsion equation, T upon J is equal to G theta over L, cross multiply over here. So T multiplied by L will be equal to J into G into theta. Transfer this theta on this side, so it will be T upon theta, and L on this side. So T by theta is torque required to produce unit angular deflection, that is torsional stiffness, that is Kt. Torque is in Newton meter, theta is in radian. So Kt is known as the torsional stiffness, that is Gj by L. Now for springs in parallel, suppose we are considering a mass which is supported by two springs which are in parallel, then total load is shared by, some part of the load is taken by spring 1 having stiffness K1, and another part is shared by spring 2 having stiffness of K2. But we know that w k is equal to w upon delta. Instead of x, now we are using delta over here. So load required to produce unit deflection. So w will be equal to k delta. Substitute that value. So in place of w, it is k delta. Over here, it is k1 delta plus k2 delta. So deformation is remaining same. Only stiffnesses are different. So delta throughout will get cancelled out. So we can say that when the springs they are in parallel, the resultant stiffness of the spring will get add up. If there are three springs in parallel, it will be k1 plus k2 plus k3. So k is known as the resultant stiffness, and k1 and k2 they are the stiffnesses of the individual springs. Similarly, if the springs they are in parallel, then what will happen, that we'll see. So delta will be equal to delta 1 plus delta 2. Here total deformation will be deformation of first spring plus deformation of the second spring. But k is equal to w upon delta. So delta will be equal to w upon k. So that value we can easily substitute. So as load shared is same, that w will get cancelled out throughout. So we can say that 1 upon k will be equal to 1 upon k1 plus 1 upon k2. Or just cross multiply this. So k2 into 1, that is k2, plus k1 into 1, that is k1, divided by straight multiply. So it is k1 k2. Take a reciprocal of this because we have to find out the value of k. So it is k1 k2 divided by k2 plus k1.